Hi, class. This is section 8.3 for finite math, soon to be called applications of business. Okay, so 8.3 is conditional probability, intersection, and independence. So we're still doing probability, and now we're going to start doing conditional. So they're like based off of each other is kind of the idea. So the first idea is a conditional probability has the notation of the big P, which always which always means probability, capital P, and this is A given B. So the probability of the occurrence of event A given the occurrence of another one, B. So what's the probability of you getting an A given that you came to class every day? So those are the kind of ideas. So this probability is actually more realistic and useful than a lot of the others. So the formula, so there's our symbol again, is it's the intersection of the two, so what they have in common, divided by the second event. Okay, the full probability of that second event. You take a second, pause the video, write that down. Okay, so let's say we have a spinner, and these are the probabilities for our spinner. So we get 1 through 6 on the spinner, and our probabilities are given here. And remember, they have to add to 1 to be a complete probability table, and they do for this one. What is the probability of landing on a prime? I always have to have my coffee. So what are the primes? The primes, 2 is prime, 3 is prime, and 5 is prime. 1 is not considered prime. It doesn't meet the definition of being divisible by 1 in itself because it doesn't have itself. It's just 1 and 1. So it's kind of a weird one. So those were our 3 primes. So the probability of a prime is going to be 0.2 plus 0.1 plus 0.3, which is 0.6. Okay? So they're still fairly normal from this chart on that question, something we've done in the last section. But what is the probability of landing on a prime given it landed on an odd? Okay, so the probability of landing on a prime given it landed on an odd. So what's the second one? Odd. So we're going to do the intersection divided by the probability of the odd. So odds are 1, 3, and 5. And the probability of the intersection of the two are 3 and 5. So the numbers that are both prime and odd are 3 and 5. So I know that I would do the intersection of the two, but I have the probability of the 3 and the 5. So I have to add those together because you could be one or the other, add them. And the probability of an odd would be the probability of the 1, the 3, and the 5, the 3 odd numbers added. And then we're going to add those up and divide and get 0.8. So conditional probabilities brings in pretty much everything we've learned with union, intersections. It might even have permutations and combinations involved as well. So what is the probability of landing on a number greater than 4 given it landed on an even number? Let's do this next one. So what is the probability of landing on a number greater than 4 given that it landed on an even number? So which numbers are greater than 4? 5 and 6. And the even numbers are 2, 4, and 6. Okay, so what are we going to do? We're going to figure out those two first, just the idea of those. And then the intersection of these two sets is just the number 6, which has a probability of 0.2. Okay, so the intersection is 0.2. Then we have to divide it by the probability of just that second set, which was, is it even? So even is 2, 4, and 6. So we add up 2, 4, and 6, and we get 0.5. So that'll be our denominator, right? And our numerator is 0.2, and then we divide to get the 0.4. Okay, 1, 2, 3, 4, 5. Okay, so here's a chart. A lot of things are given to you in some kind of a chart form here. This is accident A, or accident, which is just A, not, that's the letter for accident I meant to be. And then no accident is not A, so it has a little apostrophe on the top. And then you have your total. So these are our probabilities of you having an accident in the rain, no rain, no accident in the rain, and no accident with no rain. And then they totally add to 1, which they should. Okay, that's our probability. So what is your sample space? I just thought that would be a good thing to think about. Our sample space is rain with accident, rain with not an accident, no rain and an accident, and no rain and no accident. Okay, so what if we want to find the probability of an accident, rain or no rain? No given. We didn't ask given. So we're just going to read our chart. So what's the probability of an accident, rain or no rain? It would be this one plus this one, which is the 0.04. Sometimes they don't have the total lines on there, like this and this. They might just have those 4, and you'd have to actually add them. But some of them do give you the total. So we can just see that the probability of an accident is about 4%. I don't know if this is accurate or not. A lot of times they look up real data, but I'm not really sure. So what is the probability of an accident given there's rain? Okay, so pause, try it. Are you picking the right numbers? Are you understanding what goes on top and what you're dividing by? Okay, pause, do that. Okay, what should you have gotten after you unpause? You should have thought of it's an accident given rain. Okay, accident given rain. So we want, where are they in common? So the accident given rain is going to be the 0.025, where they both meet. That's where they are in common. And then the probability of rain. So then I have to go up here, and a probability of rain is 0.36. So we add up both the rains and we divide those. And the probability of getting in an accident given rain is 0.069, or about 7%. So it's a little higher to get in an accident with rain for the probability. Okay. All right, so another rule, and I picked tried to pick very different examples for each of these, just so you see all the different kind of types. That's the hard thing about probability. If you have the word given, you're going to follow the conditional. And again, they mix not given and given. So here's another one that we can use, this idea of the product rule. It is, if we are asking the probability of an intersection, we can find that by the probability of the first one times the probability of the second one given the first one. Okay? Or if we do the probability of B times the probability of A given B. So notice this one and this one are matching, and this one and this one are matching, and they'll both give you the right answer, or the same answer. So another way to find the probability of an intersection of two things, they call this the product rule. Pause, write that down, you might need it. So let's look at this next example. So I'm going from a chart to words. If 60% of a store's customers are female, and 75% of the female customers have credit cards at the store. What's the probability that a customer selected at random is a female and she has a store credit card? All right, first of all, what's your sample size? It's all customers, right? Or I guess I didn't say number, but what is our sample? I'm thinking of the wrong word, but anyway, I'll think of it in a second. So then we have our F is going to be our female customers. C will be our customers with store credit. So let's think through this. What is the probability of being a female customer? Well, it's 0.6. What is the probability of being a customer given your female? They gave us that, right? Are female and, okay, stores customers are female and females have credit cards. Oh, C is credit cards, right, sorry. So this is, I was thinking customers, but it's actually credit cards. So having a store credit card given your female is 75%. So what is the intersection? We can do that as the 0.6, the probability of the female times this one. So we can times those together, and that's going to give us the probability we're looking for. A lot of times in probability, we can times our answers and get our solutions. This is just another example of that. Similar, 80% of the male have a store credit card. What's the probability of a male with a credit card? Okay, so we know the probability of a male is 0.4. The probability, and that was given to us because females are 60, males are 0.4, okay? You have to be male or female. I know it's a big controversy, but you have to be male or female. Okay, so probability of a male given you have a credit card was 80%. So we can do this one as timesing those as well. I thought this should be written the other way. Pretty sure it should. I think I wrote that backward. Either way, you're going to times those ideas together. Okay, independence. The idea of independence is you can find the intersection by timesing two probabilities if they have nothing to do with each other, if they're independent from each other. So if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to B, then it's considered independent. Okay, so if the intersection is A times B, that's one way you can check it. Or checking it as if you do the probability of A given B and it's A, or B given A and it's B, then you know the events are independent. So let's see. This is some notation that they give. If event 1, event 2, event 3, and so forth are independent, then the intersections equal all of them times together. So basically, you can check for independence by following one of these two rules. And I think I have an example of that. Okay. So I did this one in a chart form again. So here's my chart. A, B, C, D in your totals, and then D, E over here. So then this one would be A, D, and so forth. I don't remember what this was supposed to be of, but are A and D independent of each other? A and D, are they independent of each other? Well, what's the probability of A? 0.7. What's the probability of D? Probability of D is 0.3. Probability of A is 0.7. And so what do we do with those? We times them, and then we see, is the probability of the intersection of A and D equal to them times together. So what's the intersection of A and D? It's 0.21, which is what we got here. So we're timesing them, and then we're checking, does it match the intersection where A and D intersect? Yeah, these are independent. That's it. That's all you do for checking an independent. I don't want to spend a lot of time on that idea. Okay. So one more example. A fair coin is tossed 5 times. 1, 2, 3, 4, 5. What is the probability of getting a tails? It's 0.5 or 1/2, right? So what is the probability of tossing a coin or a tail on the 5th toss, given that the 4 tosses before were heads? It's still 1/2. It's independent. They're like each toss, it's 1/2, 1/2. Okay. What's the probability of getting either 5 tails or 5 heads? So this one's a little bit harder. So the probability of getting 5 tails is going to be that probability of 1/2 times 1/2 times 1/2. And you will end up doing stuff like this quite a bit. So it's 1 out of 32. Another way you could draw a tree diagram with 5. So you'd go heads, tails, and you would end up with 32 at the end. It really would only take you a minute to draw it. It sounds like a lot, but it would have 32, and then you could see it's 1 out of 32, and 1 out of 32 would be the 2 top ones, all tails, all heads. Okay, so what's the probability of doing 5 tails or 5 heads? You would add those together because it's got the word or, we think add. Most probabilities this one and then this one, and it's going to end up being a times. Okay, so 5 tails is a times, 5 heads is a times, but 5 or for 5 tails or 5 heads is an or. Tricky a little bit. Okay, it's like I kind of feel like a lot of these ideas start with some basic idea questions and then they plop to kind of a little bit harder one. Oh, right. So I think that is what I have for you. Okay.